Hello and welcome to another session in physics. In this session we'll be looking at the topic wave-particle paradox. Wave-particle paradox. But before that, let's review our previous lesson. Welcome back. Now let's talk about wave-particle duality. Well, the principle of wave-particle duality explains the dual nature of matter as a wave and as a particle. The dual nature of matter as a wave and as a particle. You know, dual means two. Dual means two or double. When we say dual, we mean two or double. So basically, when we're talking about wave-particle duality of matter, we are talking about the ability or property that matter has to exist in a double form. First, as a wave, and secondly, as a particle. Alright, let's talk about light, the duality of light. The duality of light. You see, light is an electromagnetic wave which radiates out from its source with a velocity of 3 times 10 raised to the power 8 meters per second. Now, this can be used to explain the concepts of things such as reflection, refraction, interference. Yes, reflection, refraction, interference. We even have polarization, and we also have diffraction. All those things are properties of light. So the duality of light can help us to explain those concepts. And to explain other concepts such as emission, absorption of light, photoelectric effects, radiation of energy by heated bodies, all these things are things that have to do with light's electromagnetic energy. So, to help us understand these points better, it is assumed that light energy travels through space in the form of what we call concentrated bundles of energy. Like we mentioned earlier, these concentrated bundles of energy are called photons. Now, each photon is assumed to have an energy E, which is given by this equation. In our previous lessons, we've encountered this equation, time without number. It means E, energy of the photon, which is equal to hf, where h is Planck's constant and f is the frequency of the electromagnetic radiation. Now, according to Planck's theory, h is Planck's constant, and then we say because of that it helps to highlight the particle nature of light. And that's exactly what you see in this diagram here. How light behaves like a wave-like particle. Light behaves like a wave-like particle. Alright, at this point, let's talk about the duality of matter. Let's talk about the duality of matter. Now, the duality of matter, according to Newton's theories and laws, considering matter and electrons as particles. De Broglie postulated that an electron mass moving with a velocity radiates energy at a certain frequency and wavelength. De Broglie was making reference to Newton's theories and postulations and the laws that Newton made, which considered matter and electrons as particles. So, consolidating further on what Isaac Newton said, De Broglie went on to say that an electron mass moving with a velocity, a radiation, and many other things gives out energy at a certain frequency and a certain wavelength. So frequency and wavelength is very important for electrons moving with certain velocity. This principle is true for electrons and other elementary particles such as protons and neutrons. At this point, let us look at Heisenberg's uncertainty principle. According to Heisenberg, he said that it is not exactly possible to get the precise measurement of both the position and the momentum of an atomic particle at the same time. So Heisenberg said that if the electron position, which is x, is measured to a high degree of accuracy, then the simultaneous measurement of the momentum will be to a very low degree of accuracy. But basically, the main principle of Heisenberg's uncertainty principle is that it is impossible to get the precise or exact measurement of both the position and momentum of an atomic particle at the same time. So if the position is x and let's say the momentum is p, it is not possible to get these two things simultaneously at the same time. You can only get the position, or you can get the momentum at any point in time. Two of them cannot be found simultaneously. Alright, so Heisenberg's uncertainty principle went ahead to state that if the change in x is the uncertainty in measuring x and change in p is the uncertainty in measuring p, then their product is equal or greater than h being Planck's constant. Simply, what Heisenberg was saying is that change in x multiplied by change in p is greater than or equal to Planck's constant. Now, let's look at the application of Heisenberg's uncertainty principle. The application of Heisenberg's uncertainty principle. Now, the uncertainty principle can be applied to the measurement of the energy E of an object at any particular point in time. Now, if the uncertainty in the energy is known as AE, for instance, and the uncertainty in T is known as AT, the principle is represented using what we see here as the energy multiplied by the change in time greater than and equal to Planck's constant. So in all the above equations, you note that change in x, change in momentum, change in energy, and change in time are the uncertainties of position, momentum, energy, and time respectively. Also remember that momentum is equal to P and mass is m, while position is x and velocity is v. At this point, let's look at this question that says, if the uncertainty in the measurement of the position of a particle is 5 times 10 raised to the power minus 10, we're asked to calculate the uncertainty in the momentum of that particle. If the uncertainty in the measurement of the position of a particle is 5 times 10 raised to the power minus 10, we're asked to calculate the uncertainty in the momentum of that particle. Remember that for this particular question, the solution is going to be, first of all, we need to identify our uncertainty in position. So uncertainty in position is a change in x, which is equal to 5 times 10 raised to the power minus 10 meters. And then of course Planck's constant, which is h, is equal to 6.6 times 10 raised to the power minus 34 joule second. So from the uncertainty principle, from uncertainty principle, we have this equation that we wrote earlier, change in x multiplied by change in momentum greater than and equal to the Planck's constant. So therefore, uncertainty in momentum, which is what we're asked to calculate, uncertainty in momentum means we have to make the change in P, the uncertainty in P, the subject of the equation. So when we do that, we're going to have Planck's constant, divide both sides by change in x, or change in position, uncertainty in position. So Planck's constant gives us 6.6 times 10 raised to the power minus 34, all divided by the uncertainty in position, which is 5.0 times 10 raised to the power minus 10. So applying the law of indices, the uncertainty in position is going to give us 1.32 times 10 raised to the power minus 24, because when this minus 10 comes up, it becomes minus 34 plus 10, which gives us minus 24, and its unit is the Newton second. Thank you so very much for joining us in this lesson. To review or refresh your memory on what we've just discussed, please take the test that will soon appear on your screen.